Okay, welcome everyone to this continuation of what is algebraic geometry. Today I would like to tell you about the weather on Earth. I mean, literally, it's all about the weather on Earth. Actually, all of algebraic geometry is about the weather, I guess. Well, maybe not. But this one certainly is. And I do it under the disguise of what is a sheave of modules. And I will remind you what a sheave is. And I will tell you what's going wrong. Because there's one key example which does not fit into our definition of sheaves. And that's like bad. Because it's such an important example. It's like the example if you want. And if something doesn't fit into your framework, but it almost fits, then you might want to make it fit. And this is exactly where or what we are going to do in this video. So a reminder on sheaves. So sheaves is this idea to attach some data to open sets. Yeah, so really in some compatibility condition, like whatever, about intersections and so on, right? So really just attach some data to open sets in the topological space. And what you really do in algebraic geometry is you attach rings, and specifically the rings of regular functions. And they behave nicely, and everything was like, there were restriction maps and so on and so on. It was really nice. But the problem is that not all nice examples fit into this framework. Yeah, clearly not all examples fit into this framework. But if there's a specifically nice example, which you don't fit, but it looks like it should, as I said, you need to make it work. And this is the following example, and this is like key, like really key. And I stole this picture from, so it's really a good picture from Gartman's lecture series, which I'm actually, let's zoom in a little bit, which is actually really, really readable. And this is like the best picture I've seen ever of the so-called tangent vector field on P1. So P1 is a sphere, whatever you see here. Come see that in a second again. It's also called the tangent sheave. So essentially, you can literally see that at every point you attach, well, maybe that's not a good color. At every point you attach like the tangent space, like the tangent open set if you want. And like a tangent vector if you want. A little vector. And you can think of this as, well, let's do it for a curve, then the tangent is a 1D thing. Just don't be confused. A complex curve as a 1D object is two-dimensional as a real object. So what you see actually works out well. And anyway, so maybe we want to use that because it literally has this property of being defined on open sets built in to define what people could call, or what people would like to call, or people call actually, a tangent sheave. Yeah, and the tangent sheave is essentially a collection of little vectors at each point that behave nicely if you vary it over the curve, right? So when we have some smooth setting, so you kind of vary it nicely over the curve. It's kind of this tangent vector field idea. And this really looks like, if you do it, this really looks like this is supposed to be a sheave. It has this open property built in, attached to open sets. It has this gluing property built in. So it really looks like a sheave. And that's such a key example. So tangent vector space is such a key example. It kind of comes up everywhere, not just in algebraic geometry. So weather is a tangent vector field if you want. So here's a really, really nice animation, which I obviously just stole. This is a very good tangent vector field. It varies continuously, right? It varies nicely over over the sphere. Come back to the sphere in a second. It's a bit depressing how the wind is here over South Africa. That's clearly not South Africa. South America. Oh, this is quite heavy. Is someone living in this area? I realize now that I was never in this part of the United States. There seemed to be quite some heavy wind. Anyway, I guess it was a tangent. A tangent to a tangent. So weather is a key example. It's just everywhere, not just in mathematics. It's just such an important example. And it looks like it should be a sheave. The problem is, it's not quite a sheave. Yeah? In this case, let me just say that P1 is S2. So the picture you see here is like, the easiest example of a projective curve is P1, and this is S2. So weather is actually one of those examples that should play a role in algebraic geometry. The problem is it doesn't fit into what we have done, because it's how to multiply tangent vectors. It's not a sheaf of rings. Yeah? Tangent spaces are not rings. They're just vector spaces, but they're vector spaces with one additional property. They actually have an action of the ring of regular functions on it by just, well, pre-multiplication, but just multiplication. Yeah, so maybe that's what we should do to make this example work in algebraic geometry. And that's exactly what you do. And you just define it to be, and usually people call it a sheaf of O modules, OV modules, so where OV is the ring of regular functions. And it's really just the same. It's a pre-sheaf such that everything has now an action. Remind you that a module is nothing else than an action, like in this picture, where the group acts on the street sign here by rotating the vectors. You can do the same definition for a ring, and then you have a module of a ring. So the ring acts on a vector space, and this is exactly what it is. And you just define this to be, well, having the two conditions that to every open set you attach a module of our favorite ring, the ring of regular functions, such that all restriction maps are module maps. And that's it. And then tangent vectors, the tangent vector fields, is a key example, and maybe actually the example of such a sheaf of OV modules. It's not the only example, there are other examples, but I should say it's like by far the most important example that you will see. The other one, which is reasonably important, and also in case you don't remember what a module really is, maybe this one is a bit easier, is the sheaf of ideals, where ideals really have this funny condition. In case you remember, like the even numbers is an ideal. Why is the even number an ideal? Because whatever number you multiply with it, it still is even. So the numbers divisible by 3, they don't have a name as far as I know. Ternary numbers, maybe not. They are whatever. If it's divisible by 3 and you multiply another number to it, it's still divisible by 3. And that's this idea of having an ideal. An ideal naturally is a module, because whatever you multiply to it stays inside. It's just not a vector space a priori. You just want to make it additionally a vector space, and in this example of having a sheaf of ideals is like the same as a sheaf of module. So a module is really nothing else than a linear version of an ideal, if you want to think about it like that. So you can really multiply things and you stay inside. So the sheaf of ideals is like, if you linearize it, is the second example. Just this one is a little bit more exciting. So in this case, then no need to linearize anything, because a tangent space is already a linear space anyway. I hope you enjoyed this video, and I also hope to see you next time.